Hi, Slava. Good to see you.
high dimension things. And please, if you have a question, don't forget to ask for the microphone first so that the question is also recorded. Thanks.
Okay, thanks very much for the introduction, and thanks very much for the invitation to speak here. This is actually the first time in my life I'm in the Southern Hemisphere, so it's very exciting. The title of my talk is High Dimension Operators for High Dimension CFTs. And this is based off of a paper that appeared maybe a couple of weeks ago with Jae-Ha Lee, who's in the audience, so any really tricky questions I get, he'll answer for me, Hiroshi Oguri, and David Simmons-Duffin. So before I get into the meat of the talk, let me just start with the big picture question of what we're going to ask in this talk. The question we're going to ask is, what universal features do all CFTs have? Now, in 2 dimensions, in CFT2, the entropy, the dimension of the entropy of high dimension operators for a CFT is famously universal. So in CFT2, we have the density of states with some conformal dimension delta and spin j is well known to be approximately equal to this formula here. There's a parameter c called the central charge, and then the form as a function of delta and j is completely universal, and it takes this form. So as long as the twist is very, very large compared to the central charge c, the entropy of all local operators takes this universal form up to some non-perturbative corrections. And this is called the Carty formula. So this is true in 2-dimensional CFTs. And this is most famously derived using modular invariance of the genus 1 partition function. So if you write the partition function as a trace sum over all the operators weighted by their dimensions and their spin, this torus is invariant under some large diffeomorphism. And from this, you can it's like a textbook derivation that the high energy density of states has this universal form. Okay, you have to be careful how to define this. You have to smear appropriately, et cetera, and you can ask what the corrections of this are. But this general formula is universal, and it's true for all CFTs. It's true for the Ising model, and it's true for holographic CFTs. It's true for all CFTs, but for holographic CFTs, there's a particularly beautiful interpretation of this Carty formula, which is that the entropy, the log of rho, of delta and j, is roughly the area of a spinning BTZ black hole. Where the mass and the spin are basically delta and j in appropriate units. Okay, so this is one universal feature that all 2D CFTs have. Another universal feature that 2D CFTs have, which was actually discovered somewhat more recently, is that their OPE coefficients are also universal. So in particular, the OPE coefficient squared of 3 heavy operators, heavy meaning large compared to the central charge, takes this following universal form. So I'll write the formula, and then I'll say some words. So the OPE coefficient squared of 3 Virasoro primary operators takes this form. Here I assume that they're all scalars and they all have similar conformal dimensions, but there's a more general formula you can write down where you give them spin, and they can have different dimensions and different spins. I'll also say in passing that there's also universal formulas for heavy, heavy, light, and heavy, light, light OPE coefficients of the Virasoro primaries. And this you can derive by looking at modular invariance of the genus 2 partition function. As was done by these guys in 2017. So the question I'm going to ask in this talk is, so we have all these wonderful universal features for 2D CFTs. You can ask in d bigger than 2, are there similar universal formulas? both for the entropy and for the OPE coefficient, the 3-point functions. So one reason that you might hope that it's reasonable to hope that this is the case is that for holographic theories, these formulas have some nice black hole interpretation, and black hole physics is also universal in not just in ADS3 but also in higher dimension ADS. So that may be one intuitive reason why you might hope that there should exist some universal formulas. But the math, of course, is different. So in 2 dimensions, both of these results were derived using modular invariance of genus 1 and genus 2 partition functions, and obviously we don't have that luxury in higher D. So if you look at the partition function, for example, on S d minus 1 times S1, there's a famous theorem in mathematics that says d minus 1 is only equal to 1 when d is equal to 2. So the math is different. But in this talk, I'll just tell you the answer now, and then I'll get into it. The answer is yes, there are a similar universal formula for the density of states as well as the OP coefficients in d bigger than 2, but there are some important differences from 2D versus higher D. So I'll say what some of the differences are, and then we'll get into it later in the talk. So one is that in 2D, the entropy is just determined by one number, which is the central charge C. Right? So in this formula, there's just one parameter C, which of course it has other interpretations. But for the purposes of this talk, we can think of it as just a single real parameter that then determines the whole functional shape of the leading order of the entropy. And the corrections are then non-perturbatively small in delta. In higher than 2D, we'll see there's an infinite set of perturbative corrections. Well, infinite set of parameters, which each of them gives you sort of the next order in perturbation theory. Okay, another difference, and this will be more relevant for the OP coefficients, is that in 2D we have Virasoro symmetry, which is an infinite dimensional symmetry, but obviously in higher D, we'll only have the global symmetry. So we'll only look at global primaries. And a third difference that I'll mention is that in D bigger than 2, these parameters I described here are not going to be related to central charges of the stress tensor, and they're not going to have monotonicity properties under RG flow necessarily. So in 2 dimensions, there's famously the C theorem proved by, I guess, Amologikov a long time ago, that in addition for this central charge being, this parameter in the Cartes formula, it always decreases under RG flow. So the theories in the IR always have a smaller C than in the UV, and these parameters will not necessarily have any RG monotonicity properties. But despite these differences, there's still going to be some universal formulas for things like the entropy and the OP coefficients for higher D CFTs. So that's where we're going, and let me then just sort of get into the meat of it. The main technology, the main tool we're going to use is a tool that's sometimes called thermal effective theory. And the idea of the logic is the following. Let's consider our d-dimensional CFT, where d is bigger than 2, and we'll imagine compactifying it on a circle. So we'll imagine putting the CFT on an S1 with some size beta. And the main point is the following. Because this is a CFT and we put it on a circle, there's actually no parameters we can tune, because the only parameter we have is the dimensionful parameter, which is the length of the circle. So there's nothing you can tune. So generically, if you want to view then the circle as very small, the d-1 dimensional theory you're going to get is going to be generically a massive quantum field theory. It'll be gapped. Of course, there's going to be some exceptions. If the theory you started with is free, for example, then you can have a gapless sector, is S1. Or if the theory is supersymmetric and you compactify an S1 with supersymmetric, with a -1 to the F inserted in the S1, then there may also be a gapless mode. But generically, if you start with the 3D Ising model and you just put it on a circle, you're going to get a gapped quantum field theory. And so the correlation function of this d-1 dimensional theory will decay exponentially at large distance with some correlation length C. And by dimensional analysis, xi has to be proportional to beta. And we're going to view this gapped theory as a kind of modular dual. So the magic in 2 dimensions is that the modular dual of the theory is the theory itself. But in higher dimensions, we're going to pretend that we're going to treat this d-1 dimensional quantum field theory as a way of probing the high temperature behavior of the partition function. In particular, this is a gap quantum field theory. So the idea is that we're going to couple our original CFT, our original d-dimensional CFT, to some background fields, in particular a background metric. And we're going to write the partition function of the gap theory as a function of these background fields. Because this is a circle compactification, we can always put this metric in Kluzik-Klein form. I'll write that over here. In terms of a metric and a gauge field and a dilettante. And the partition function of the CFT as a function of this metric is just the gap theory as a function of now a metric, a gauge field, and a scalar. And now the lore is that this gap theory can be captured by some local effective action as a function of the d-1 dimensional fields. So z gapped of g a phi is some e to the minus s thermal effective action of g a and phi. And I should say, this is an old idea, and actually I think it was used very effectively in the hydrodynamics literature by people like Bhattacharya, Menwala, and others some years ago. There are, of course, errors here that will be non-perturbative in the correlation length. And the way we're going to make our money from this thermal effective action is that this thermal effective action is highly constrained by the symmetries. So symmetries constrain S thermal. So here are some symmetries that we have. One is that we have d-dimensional coordinate invariance in the original CFT. And in the usual Kaluza-Klein compactification, this translates to d-1 dimensional coordinate invariance in the metric and gauge invariance. We also have Weil invariance of the original CFT, which is that the CFT, the original CFT, when you rescale by a Weil transformation, the partition function remains the same up to a possible Weil anomaly. It depends on the dimension that you're in. And what this implies is, up to this Weil anomaly term, your thermal effective action is just going to be a function of the gauge field and this combination of the metric and the dilettante, minus 2 phi times g. So we could then write the most general possible thermal effective action based on these principles. And this thermal effective action will parameterize this quote-unquote modular dual of our d-dimensional CFT, which will allow us to then read off the high-dimensional data. So the most general thermal effective action we can write down is d-1 dimensional action. And now we can just write down all of the terms in the effective action that we would do in just the usual Wilsonian, Wilsonian picture of quantum field theory. So we could write down a cosmological constant. My convention is I'll put a minus sign here, just for convenience. And then we write down all terms we can build from these fields. So we can write down an Einstein term. I put this hat, meaning I use this g hat instead of g. We can write down a Maxwell term. And you can keep going. You can write down like Einstein squared. You can write down f to the fourth, whatever. And we use these unknown coefficients, these unknown Wilson coefficients like f, c1, c2, to parameterize our ignorance of what the d-1 dimensional quantum field theory looks like. Oh, and there's also a Weil anomaly term. This will depend on like A or C in 4 dimensions, for example. And this depends on, in odd dimensions, this won't be there. Now, the point is that we're going to parameterize all of the universal CFT data in terms of these infinite set of unknown Wilsonian coefficients. And these will kind of play the role of the central charge C in the 2D CFT. So these infinite set of coefficients will parameterize like the high energy data of the CFT in a way that I'll make clear.
Sorry, just
Yeah.
to clarify, this extra term is to match the anomaly.
Exactly, exactly.
You can repeat.
Oh, sorry. The question was, what was the point of this as vial, and it's to match the vial anomaly. Yeah. So this would depend on like A and C, for example, in 4 dimensions and things like this. Okay. So
are you ever going to write some terms which will depend on the correlation length because they're higher?
Oh, I'll talk. Good. You mean like the corrections that the non-perturbative corrections?
I don't know. Sure, perturbative. Suppose that there is some higher derivative term. How are you going?
Like you mean like r to the 4th, for example, or r squared?
Yeah. Yes.
Yeah. We can include these as well. Yeah. So this would be in the dots.
Yeah, but what is going to be the coefficient of that term?
We can call it C3 or.
Yeah, but C3 it doesn't have the same dimension as C2, so there has to be some scale that you will introduce.
Is it out of periodic or beta periodic? That's another way to phrase the question.
Sorry, I couldn't hear you.
I think another way to phrase the question is whether tau is pi periodic or beta periodic.
No.
You're absorbing it in pi or not.
Is tau periodic? Tau.
No, I'm asking a much simpler question. Sorry, Gabriel. I'm just saying, so C3 doesn't have the same dimension as C2 or C1.
No, these will all be dimensionless
Dimensions?
parameters.
Well, it doesn't have the same number of derivatives.
Yeah, there's only that's right.
Yeah, then I don't understand your conventions. Sorry, you have to explain a bit better.
So it's sorry. Give me 1 second. Well, yeah, I guess these are the units are made up by the betas. Yeah. So indeed these higher dimensions. Yeah. Sorry. Very good. We'll see that these higher dimension terms, because their units are less, they'll have extra powers of the temperature of beta.
Why not Xi?
We're taking Xi we're assuming this. We're taking the very long distance limit.
No, but this effective theory should be valid provided that variation of the gauge fields and the metric.
Yeah. Xi is like beta. This is beta.
No, but there could be some proportionality factor which doesn't have to be order 1. So you're assuming that the correlation length is really. You're assuming there's no big hierarchy between beta and Xi.
Yeah. I think this is an assumption.
Okay.
Yeah.
Okay, fine.
Yeah. Thank you. Yeah, we'll see. Yeah, sorry, but yes, we'll see that these terms. Sorry. These higher derivative terms will have extra t's, temperatures, or betas, and we'll see that explicitly later. Yes. When I said non-perturbative corrections, I mean corrections on top of the derivative expansion. That was she's comment or question. Am I still audible? I'm not very good at it.
Topologically normal, it's not like that. But if it works,
Okay, it'll work at least in the short time scale. Maybe in long time scales there will be some corrections. Very good. Okay, let me make a brief comment from this perspective. Why, in this thermal effective action perspective, 2D CFTs are special, because of course, one reason 2D is special is we have modular invariance, et cetera. But from this, we can also see another reason why 2 dimensions is special, because in 2 dimensions, we cannot write down these higher derivative terms. Right? So in 2 dimensions, this thermal effective action is just controlled by one number f, which is then going to be related to the central charge c. So why is 2D special? There are 2 answers. One is that the first answer that we gave is you have modular invariance. But the second answer is that the only local gauge invariant term you can write down is f, the cosmological constant. So that means that there aren't these perturbative corrections to the, we'll later see that these all induce corrections to the density of states that are suppressed by powers of delta, and we'll see that these just aren't there in 2 dimensions. So from this perspective, we see why 2D is special. Okay. So now let's use this technology to compute the density of states for the CFT. So what we're going to do is we're going to put our CFT on a cylinder. So we're going to put it on an S1 of size beta times SD minus 1. But we would like to keep the spin dependence. So what we're going to do is we're going to twist by the angles of the sphere. So when we go around by this beta, we're allowing a twist in the angles. So yeah, go ahead. I can't see who is asking a question.
You should get the microphone.
The question is, why is this effective action necessarily local?
As a function of the fields?
Yeah.
Well,
Because I imagine you're integrating out, the fields of the theory, right, of the CFT.
that's right. That's right.
And you
Yeah.
said that there may be massless modes in there.
I'm assuming that the theory, when put on a circle, does not have gapless modes. Like this won't be true for in general. Like for
But
free
if it
theory,
was a
this may
free
not be
theory, for example.
true. Yeah, for free theory, it's not going to be true. For free theory, it's not going to be true. But for a general interacting CFT, we would expect it to be true. But you're right. For free theory, it's not true. And indeed, we'll see. I can discuss. If we try to apply this for a free theory, we'll see exactly where it breaks down, because there will be a gapless sector.
All right, thank you.
Yeah, thanks for the question. OK, so this is the geometry we're going to put our theory on. And we're going to compute the partition function as a function of the temperature and these angles. So these omegas are the parameterize the different angles. So in high dimension, there could be like d over 2 of these. This is the dimension of the Cartan of SOD. So this is the partition function, graded by both the dilatation operator and the spins, the angular momentum. And we're going to say that this is given by e to the minus s thermal as a function of the background fields. So all we need to do then to compute this partition function is compute the thermal effective action in this geometry we described here. And the way we do that is simply we put the manifold inclusive Klein form, we read off the metric and the gauge field, and we literally then just compute these integrals explicitly. So this is a calculation that you can do, and here's the final answer you get. As thermal is given by the following. And this is what we're going to read off the partition function, the canonical ensemble partition function, as a function of these Wilsonian coefficients f and c1, c2, et cetera. So let me say a few words about this. First, we see this is a function of the temperature, 1 over beta, and these chemical potentials. And we see here where the Wilsonian coefficients enter. Here's f, the cosmological constant. C1 was the Einstein term. C2 was the Maxwell term. And these higher derivative terms will appear in dot, dot, dots. And as Slava predicted, indeed, like to make the dimensions work, we have extra powers of t to compensate. So the next term, for example, would be t to the d minus 5, coming from the 4 derivative term here. So here I wrote up to 2 derivatives. You include the 4 derivative terms, that would be t to the d minus 5, et cetera, et cetera. So from this, so let me put this in a box. From this, we can read off, well, OK, we exponentiate this. We get the partition function. And all we need to do is then take an inverse Laplace transform to get the density of states as a function of these infinite set of unknown coefficients, f, c1, c2, et cetera. Let me make a few comments about this. First of all, already at this level, we see that there are some non-trivial predictions it makes. Well, OK, this t to the d minus 1 is basically just dimensional analysis. But the omega dependence seems already kind of a non-trivial consequence, as well as the omega dependence of these higher order terms. Also, a priori, it wasn't so obvious that the expansion had to be in powers of 1 over t squared. You see here, this is an expansion of 1 over t squared, because we can only write down terms with an even number of derivatives. So therefore, we see that in the free energy, we get an expansion of 1 over t squared as opposed to like 1 over t or 1 over square root of t or whatever, which a priori didn't seem so obvious. Let me make a couple other comments about this formula here. OK, the first is what happens in 2 dimensions. Well, in 2 dimensions, the coefficients with the like the C1, C2, they all vanish, and we see there's a d minus 2 multiplying them. Which,
Sorry, I have a very basic
Yeah, please.
confusion. So those C's,
Yeah.
C1 and C2,
Yeah.
if I wanted to make them dimensionless from the beginning, I would write them as proportional to t squared, right? I would write C1 as t squared times C1 hat, and C2 as t squared times C2 hat, right? Am I right, or no?
I think in these conventions, these will be dimensionless numbers. So maybe I secretly absorbed a t squared in them. Yeah, it may be in the definition of R hat I absorbed a t squared in them. But in my convention, these will all be dimensionless numbers.
But then, how do the dimensions agree? Because you have t to the d minus 1 and t to the d minus 3. You cannot add dimensionless things.
Well, yeah, yeah, that's right. There's the radius of this sphere. Yeah, thank you.
Okay.
Yeah, thank you. It's the same as, yeah, exactly. Same as when I have a t to 1 over t transformation in 2D CFT, there's always secretly there's the length of the cylinder that we set to 1. Yeah, thank you. OK. So the first feature I would say is that in 2D, once I identify f with the central charge, we get the partition function is given by this, e to the t over 1 plus omega squared. And this is precisely the S transform of the vacuum. So this is exactly what we know from modular invariance of the 2D CFT. So this is the correct high temperature partition function in 2D CFTs. The second thing I want to point out is you'll notice that this S thermal diverges. Oh, I identified, I made this identification. Yeah. The second thing you'll notice is that there's a 1 plus omega squared in the denominator here. Let's assume for simplicity that I just turn on one of the chemical potentials, although I can turn on others. So we see that this S thermal diverges at omega equals I. And this is the right physical interpretation. This is us rediscovering the unitarity bound. The reason is we can see is we look at the trace here. Imagine omega is equal to I here. Then we see that states with a fixed twist but going to infinite spin are not penalized. They all have the exact same Boltzmann suppression. But we know that for any CFT, there's always infinitely many of such states, these so-called Regge trajectories. So we see that we better get a divergence in the partition function at omega equals plus or minus I because of the existence of these Regge trajectories. And we sort of, well, we didn't input it in my hand, and we sort of rediscovered it in this form. So this is another good sanity check. A third point I already made, which is that it's an expansion in 1 over t squared. OK, so I'll write down the explicit inverse Laplace transform for 3D CFTs. You can write down the general D, and it's a little bit annoying, but I'll just write down in 3D, because there's only one spin that we can turn on, right? Because the Cartan of SO3 is one-dimensional. And there's a log here. So this is the entropy. So this is the analog of the Cartier formula for 3D CFTs. So this is the leading term. I should say this leading term was also computed earlier in 2015 by Edgar Shiguldian in a very nice paper. So we see this is the leading term coming from the cosmological constant, and this is the one-loop determinant stuff. This is then the correction from the Einstein term, the correction from the Maxwell term, and if you wanted to keep going, you could keep going. this gives the distribution of the states as a function of their spin. So it's kind of like the statistics of spin. So if you want, you can call this like a spin statistics theorem for CFTs.
So
That was it.
there could be a Chern-Simons star in.
Chern-Simons, yeah, very
for
good. There could be a Chern-Simons. So the Chern-Simons term will show up if the CFT has something like a gravitational anomaly. So for example, if C left were not equal to C right for a 2D CFT. We could include that. We assumed there was none, but you could include it and you could compute it in exactly the same fashion.
So yeah, the question is how would it scale there, because it should be more important than the first, than C1, C2.
Yeah, that's right. It would be more important than C1, C2. That's right. Yeah.
So like, which
It would-
power? I was just curious. Do you remember on top of your head?
We didn't compute it, but we could probably read it off by, so if you set j to 0, this one, sorry, this is 1/3. This is 1/3, not 2/3. This is delta to 2/3, this is delta to 0. I think it would be delta to the 1/3. No, we didn't compute it, but I think you can read it off. Okay, let me make a brief aside commenting on some of the monotonicity properties that this does or does not have. So in 2 dimensions, the central charge, which controls this leading behavior, famously decreases under RG flow. But in higher dimensions, F does not necessarily decrease. And there are 2 counterexamples that I'll just explicitly give. The first one's only kind of a counterexample, but it's still kind of interesting, which is in n equals 4 super Young-Mills. And there, I'd say it's only kind of a counterexample because now it's going to be under marginal deformation, not under relevant deformation. But there it was famously computed by Gubser, Klebanov, and Pete in the 90s that as you go from strong to weak coupling, as you go from weak to strong coupling, F changes by a factor of 3/4. Whereas in a 2D CFT, under marginal deformation, the central charge would always be fixed. The second example is that the ON model in 3 dimensions, at large n, this can flow to a theory of n-1 free scalar fields. But F increases by a factor of, I think, 5/4. And this was shown by Sachdev in the 90s. So it's a little bit counterintuitive, because what this means is that for fixed delta and J, the entropy will be actually higher in the IR than in the UV. But it's not a contradiction or anything, but it might be a little bit counterintuitive. This will never happen in 2 dimensions, of course. Okay, let me comment a little bit about the regime of validity of this formula. So, of course, we need large delta, but the question is, how large can we take the spin so that we trust this formula? Already we see, actually, if you take the spin all the way up to delta, this term blows up. So we should not be able to take J all the way to delta. So we have to, yeah, please.
Is there any interesting, is it like a trivial to go from all states to primary states?
Oh, very good. Thank you. It's not completely trivial. You have to decompose into the conformal characters. So remember here, so we have the trace of e to the minus beta d plus I beta omega m is equal to e to this guy. So to get all states, you just take an inverse Laplace transform. To do primaries is slightly more work. You have to then invert the characters instead of the Laplace transform, you have to invert the characters. It's not that difficult because the characters aren't so complicated. You basically just form these words, but there is a step that I skipped. You're absolutely right. It won't affect the leading term, but it shows up already in this log term. And indeed, you can see this 2j plus 1. This is the size of the representation, which often shows up in these things. Yeah, it's a very good question. Thank you.
The fact there are divergences in higher order terms, does it mean that one should shift delta squared minus j squared in the first term?
Very good. We'll see that this formula is just not even trustworthy when j is close to, when j is equal to delta. When j is even, we'll see how close we can take j to delta. So that'll be precisely my next point. Yeah. I don't know what it means j is fixed. Like delta and j are both You mean in terms of smearing? Oh, yeah, good. So I'll say how large you can take J. You're asking, like, can I take J to scale with delta? Yeah, the answer is yes, but, I'll precisely answer this now. So the question is, how large can you take J with respect to delta? So to answer this question, we have to remember that the way we derived this was with a high temperature expansion in powers of in 1 over the temperature. And the way we got the density of states was at some point we had to invert the partition function against either a Laplace transform or more precisely the conformal characters. And we did this via saddle. And we need to make sure that the saddle is located at a high temperature. Because if the saddle is located at a low temperature, you don't trust the result at all. So when the dust settles, here's what you get for the regime of validity. And it's different, qualitatively different in 2 dimensions versus higher dimension. So I'll say what they are. So in 2 dimensions, it's the usual Carty regime. You need the twist to be much larger than the central charge. But for d bigger than 2, if you just turn on one spin, you need the twist to be much larger than the square root of f times delta. So what this means, to answer like Scott and Sylvia's question, is you can take j almost up all the way up to delta. Like a j can be delta over 2, that's fine. It can be like 9/10 delta, that's fine. But it can't touch delta. It has to differ by square root of delta. So if you're interested in the regime where like the spin is delta minus delta to the 1/3, then this is not trustworthy at all. Just because here we do some derivative expansion and the terms that we drop could be like more important than the terms that we keep. So it's not trustworthy at all if you're not in this regime. This formula is quite interesting also because there's a very, very interesting connection to Kerr black holes in ADS space that I'll get to maybe discuss now. So this is true for all CFTs, but now I want to apply this for holographic theory specifically.
Sorry, you said, so this comes from requiring that the saddle is at high temperature, but is there some constraints on the omegas? Are they order 1?
Yeah, the omegas will be order 1. There won't be an omega blow up with this constraint in this regime. So for holographic theories, we can read off the free energy, log z, just by doing black hole thermodynamics. So this means we can then just explicitly fit the formula we have here and solve what these coefficients f, c1, c2 are as a function of LADS. And we get these results. So this is the d plus 1 dimensional Newton's constant. And you could, in principle, go to higher derivatives as well. We just stopped here. OK, so these are the leading order terms for the Wilson coefficients. Of course, there will be corrections in powers of g Newton, and there might be corrections also in like alpha prime or whatever. But these are the Wilson coefficients from Einstein gravity. And if you like, you can think of these as kind of some higher dimensional generalization of Brown-Cournot formula. I don't mean in terms of an asymptotic algebra in infinity, but I mean like in terms of relating the central charge to the radius of curvature of ADS. This is like relating the radius of curvature to ADS to these set of Wilson coefficients. One interesting comment is this means that the ratios of these coefficients are completely fixed. These ratios are some order 1 numbers. And that means that if you have some dial in your theory that makes it go to some holographic theory, like in n equals 4 super Young-Mills theory, for example, these ratios, far from the holographic point, they can be any number as far as I can tell. But as you get to the strongly coupled holographic regime, they have to approach this order 1 number. So this could be an interesting diagnostic for a test of Einstein gravity. OK, but now I want to say how this expression here for the regime of validity has to do with these Kerr black holes. So here's a fact about Kerr black holes in ADS, which is they're parameterized by some mass and some angular momentum, and they're actually unstable if they spin too quickly. They suffer from an instability. It's sometimes called superradiance instability. This is for ADS4 or bigger. And this was actually only worked out like, maybe 20 years ago. But the condition is given by the following. So this is just a statement about Haskell GR. The black holes are stable if their mass or their energy minus their angular momentum in appropriate units is bigger than some order 1 number, which is I think 1 over square root of 2 or something, but it's not going to be important for this talk, times the square root of their mass. Now, there's a very, very similar condition as the general regime of validity that we discovered here for the CFT. There, we said delta minus j is much bigger than square root of f times delta. And delta is kind of like the energy. The j is like j. And f, recall, was like 1 over g Newton. So this looks very similar to here, where we take this 2, where we need to be parametrically larger instead of having an order 1 number that we know. So this suggests, this leads us to conjecture that there may be an extended regime of validity for our entropy to hold for holographic theories. So let me review what is known about that in 2 dimensions first. So in the case of ADS3 CFT2, about 10 years ago, there was a beautiful paper by Hartman, Keller, and Stoika that discussed an extended regime of validity for the Carty formula. So what they showed was that in ADS3 CFT2, the entropy, which is Carty's formula, is valid when the twist is much bigger than the central charge. But the condition for a black hole to be stable in ADS3 is just that delta minus j is on the order of the central charge. There's an order 1 coefficient here, which is like 1/6 or 1/12 or something like that, but whatever. And they proved, using modular invariance, that a sufficiently sparse light spectrum, which we can make precise, implies that the entropy is also trustworthy down to delta minus j on the order of c. This is Hartman, Stoika, 14. So now let's see what the situation is like for d bigger than 2. CFT d bigger than 2. There, we know that the entropy that we derived is trustworthy when the twist is much larger than square root of f times delta. And the black holes are stable in the same regime, but where we don't need to be parametrically large, there's an order 1 number, which you can solve for. So it would be very interesting. Of course, we can't prove this because we don't have modular invariance to prove all these wonderful things, et cetera. But it would be very interesting if something like a sparse spectrum or some other nature of some other measure of holographic CFTs would imply that our entropy is trustworthy for an extended regime of validity. So I think this is a very natural conjecture to make, but of course, we're not able to prove it. But I think this would be very interesting, just as a pure CFT statement. Like if you have a theory with a large number of degrees of freedom, and the sparse spectrum grows slower than maybe Hagedorn or something like this, then this entropy is universal all the way down to here.
So the regime of validity, you got it from analyzing the saddle point.
Yeah.
So what happens to the saddle point when you go to this regime that you're discussing now?
If you go out, you mean outside of this regime?
Yeah, outside, but still inside.
Yeah, then the saddle's at an order 1 temperature. It's not controlled by. Yeah, I don't have it. Well, yeah, one can explicitly write it down, but you'll see that this saddle is not parametrically large. Like it doesn't scale with delta or anything like this.
But does that give you any intuition of what low dimension operators would do in this type of geometry? Because if you think
Oh.
that you have the higher dimensional CFT in this background, why the sparse spectrum would help you there? Or?
Oh, the reason I just say sparse, I don't know if sparse spectrum is enough. I don't know what it is, but just that the only reason I say this is that for theories dual to Einstein gravity, I would expect the same functional form to be valid all the way down here, just from the black hole physics. So I think there should be some condition that's holographic, maybe some HPPS condition, something like this, that would imply that from just a pure CFT statement, this entropy has extended regime validity. So maybe something like sparse spectrum, maybe you need more, maybe I don't know, like chaotic behavior of some other type, whatever, but some nature
No,
of
but I
holographic.
mean, I was asking if the shape of the saddle point could already give some hint of that.
I'm not sure, because I think if the saddle is at some order 1 number, like it just doesn't make sense to even do this from effective action. But yeah.
So it's fair to say that it's unclear what the higher D analog of identity block or identity character dominance is? Because that's why you need the
Right,
sparse
yeah,
spectrum
yeah.
in this
Well,
case.
yeah, because of course, as you know, the point of this was that then this identity character dominance, you could do an S transform and then do this. So I don't know what,
Here
I
the
don't know.
connection to the CFT data of the data of the original CFT is a bit unclear.
Yeah, it's not, well, it's certainly not something so nice as just take an S transform and go about your business. Maybe there is something like some identity block, but of course it's hard to say because of course we don't have a Virasoro symmetry, so the identity block is also much more pathetic in higher dimensions as well. Yeah. Oh, I am. Very good. Thank you. Sorry, let me repeat the question. The question is, in general D, am I not distinguishing JIs? Because, of course, starting at 4 dimensions, there'll be multiple Js. You're right, I was being a little bit sloppy. Here, I assumed I only turned on 1 JI, but you can do this analysis if you turn on more general JIs, and this squared will change. In particular, if you turn on, let's say, m of the different JIs, and you take them all to be large, like scaling with delta over m, this coefficient will be like 1 over m plus 1, both here and here. So, but yeah, thanks. I was being a bit sloppy. So, if you turn on multiple spins and the condition for the black hole being stable and for our entropy formula to be valid is the same functional form. And again, the only difference is these 2 greater than versus 1 greater than signs. And I actually think this is kind of remarkable because, at least a priori, it looks like these are completely different calculations. But somehow it always gives the same structure. So maybe it's a red herring, but I think it's kind of interesting. Yeah. Any more questions? Yeah. Thanks for all these questions. Okay. Very good. Let me say one more comment about this general form. Another thing that we did just as a sanity check of our results is there's a lot of numerical data computed by like many people in this room about, for example, the 3D Ising model. And in particular, a lot of the operators have been numerically computed up to dimension like 8 or 10 or something like this. So what we did was we explicitly constructed a partition function. Of course, not all of the operators are known, like only like maybe the Z2 even ones and things like this. But we explicitly constructed the partition function as a function of their dimension and their spin and plotted it and fit it with just this leading term. And by tuning this parameter, we're able to get within a couple of percent if the temperature is quote unquote a moderate value. So you have to be a little bit careful because you can't make the temperature too big or too small. Because if the temperature is too small, then it doesn't make sense to truncate the effective theory. But if the temperature is too big, then the fact that only operators up to dimension like 10 or whatever have been bootstrapped make the partition function a very bad approximation. But for moderate values of the temperature and the chemical potentials, we get pretty good estimate for the partition function with just this leading term to the precision of a couple of percent. Okay. So, and maybe in the last, I don't know how long, 15 minutes? 10 minutes?
So is this a way to measure f, or did you know f?
Yeah, okay,
for
good,
3D Ising?
very good. This could be 2 things. One is this is a way to measure f. Another thing is if you already have f, this could then be a sanity check. And we did both of those because the Monte Carlo people also computed f. Yeah, I can say more. For the Ising model, they have f to be about 0.153. So there, if we just plug in this value of f, and we plot the partition function with these moderate temperatures, so beta between like 1 and 5, and omega less than, I think, 0.5 or something like that, we're only off by a couple of percent. But the other thing we did was we just left f as a free parameter and minimized the error. And there we get something like 0.15. So it's very nice that it's within, well, it's a sanity check that we're not saying anything crazy. What would be actually very nice is if there's like, another thing you could do is you can also fit for these higher dimension operators. These have not been estimated for the Ising model toward the best of our knowledge. Unfortunately, just from a practical perspective, it seems we don't have enough operators Bootstrap to be able to trust this term. Like you can kind of fit anything to them. It seemed, but.
Just out of curiosity, how far is this from 4/5 times f4?
That's a good question. We didn't check that, but yeah, you're saying. Oh yeah, sorry. The question was how far away is this from 4/5 times f for a free scalar? And the motivation is for the ON model at large n, it's known analytically at large n, and so this would be like whatever n equals 1. But I don't know. We didn't check that. Probably you can put this in Mathematica in real time in the last 10 minutes of the talk.
I have a question.
Yeah.
I got stuck there in the superradiance.
Yeah.
In that equation, what is the angular velocity of the black hole? What can you relate from the usual formula?
Oh, yeah. Very, very good. This formula comes from the velocity of the black hole. The instability bound is when the velocity is like 1 over LADS. It's when the black hole is spinning too fast. Yeah, and then I just converted it to canonical ensemble, the microcanonical ensemble to compare here. Yeah. So this is called superradiant instability. If you want to Google it. Say one more time. About OPE coefficients? Okay, the question was, can I say anything about OPE coefficients of the operators, which is great, because that was what I was going to talk about the last 5 or 10 minutes. Still 10? 10 minutes, great. This is some time dilation. So there's more to life than the density of states. There's also OPE coefficients. It's important to keep perspective. In particular, we're going to try to compute C heavy squared of general CFT. And the point of this will be partly to compute this, but also partly to illustrate how universal this technique of this thermal effective action is. So first, let's recall, roughly speaking, how this derivation works in 2 dimensions. So there, in 2D, we look at a genus 2 partition function, which I'll decompose in this channel. If we compute the partition function of a 2D CFT on this geometry, and let's say the lengths of these are beta 1, beta 2, and beta 3. This partition function measures sum overCijk squared of e to the minus beta, well, let's call it 1, 2, 3 squared. Beta 1 E1 minus beta 2 E2 minus beta 3 E3. And if we take the betas very, very small and perform a non-trivial modular transformation on this genus 2 partition function, again, we can roughly speaking, that takes these betas to 1 over betas. It's not entirely obvious, but that's roughly what it does. So in sort of the low temperature channels, when you can approximate this just by the vacuum propagating, and in the high temperature channel, you get the heavy coefficients. Now, if you're interested in the primary operators instead of the scaling operators, you again have to invert the blocks, et cetera, et cetera. But the point is that you can get, that's the computation that you can do. So at large beta, this is a vacuum. Then you do some modular transformation plus the blocks, and you get C heavy squared. So it's essentially a very similar argument as Cardy's formula. We'd like to generalize this to higher dimensions. And so roughly the 3 steps you can imagine you take is, the first step is you find a geometry whereCijk squareds are computed. Then you take some kind of high temperature limit, which I put in quotes, that you can compute. the partition function. And then you invert to find C heavy squared. And the inverting may be non-trivial because you may need to invert some blocks. That's important, but it's a technical aside. And so we're just going to mimic this construction for higher DCFTs that we did for 2 DCFTs. We're going to take 2 copies of RD, conformally compactified to the sphere. And in each of these copies of RD, we're going to cut out 3 balls. It's going to be convenient to make them mutually tangent. Of course, we could do whatever we want, but we're going to make them mutually tangent. So each of these has an SD minus 1 boundary. And then we're going to glue 3 cylinders. Glue these SD minus 1s on top of each other. So we have 3 cylinders here. So we have one here, and one here. Sorry, it's getting a bit messy. Oh, thank you. Thanks. No, this is much better. The partition function on this geometry, which we're going to think of as some higher dimensional version of a genus 2 surface, is computing Cij squared minus beta I. Where betas are the length of the cylinders.
Can you comment this touching balls? This looks like a singular geometry. What's going on here? Why?
Okay, we can take them some slight distance apart if you want. Yeah, I mean, we don't have to take them touching now, but it'll be clear why soon we want to take them to be very close to each other. It'll be so I can compute them.
Are the cylinders also touching or only the balls?
The cylinders don't have to be touching.
Okay.
Okay, so we would like to compute the partition function on this very complicated geometry, but we would like to use our thermal effective action technology, but this is not a circle fibration, so we don't know how to do it. The idea is the following, which is an assumption, which is, let's imagine we take the cylinders to be, the betas to be very small. So we take these 2 copies to be very, very close to each other. We see then that there's kind of an emergent thermal circle. So I'll draw it again, and here I'll use colors. So I think I have red here. If you go up one side of the cylinder and go over a little bit and down and back here, anytime we see where 2 of the cylinders touch, we see a circle emerging here. And as these betas get smaller and smaller, this circle becomes small as well. So in this part of the geometry, it looks like we have something that locally looks like a circle fibration. So the idea is that in the red region, we can approximate the partition function using the thermal effective action. And our assumption, which is not proven, is that in the beta goes to 0 limit, this is the dominant contribution of the partition function. From this, then we can, okay, it's still a lot of technical work, which I'm just going to put aside. We can then do the same thing where, again, now we have the value of the partition function. We have to compute the blocks, and we can invert the blocks, and we get some expression for the heavy 3-point function squared. And I'll just write down the final answer in 3-dimensional CFT. I also assumed here, I assume that the spin is very small. So probably one can redo this argument where we keep the full spin dependence, but we haven't done this yet. We just looked at 3 scalars with the same dimension, and we get this behavior. And this is for global blocks, of course.
Sorry, can you, I'm still very confused. Like, before you had 2 scales, beta and R, and you were taking the limit beta much smaller than R. Now you have 3 betas, 3 Rs,
yeah, good,
and
good.
the distance between the balls.
Yeah, here I'm assuming all the betas are the same.
Yeah, but you also have the distance between the balls, between the insertions you
This
count.
one,
Why
I think
does-
I want to be much smaller.
So, sorry, okay, again?
Yeah, I don't think that this. I think the distance of the balls we can take the limit to 0 and it should be okay. But I'm not.
And that doesn't create any. It's okay. So the limit's
Oh.
like distance to 0, then it's like beta much smaller than the radius of the spheres, and the distance between the ball much smaller than beta, something like that.
I think so. I think so. Beta definitely much smaller than the distance of the sphere. I guess I didn't think about the distance of the balls. Probably I want this one to be much smaller than beta.
Yeah, and
Yeah.
what does that correspond to? This physia, the distance between the balls, like, or does it enter in this C1 to 3? What's like?
No,
where does it
no.
enter in this?
I mean, betas won't enter in C123 either, right? Like C123 will just be a function of the deltas.
I mean, this partition function should depend on the distance.
yeah.
between
The
these
partition. Yeah, but yes, but this is not the partition function. This is when we invert the partition function.
Right, but you had a schematic formula for Z. Is it in that C1
Oh,
to
I
3?
see here. Yes.
Yeah, so just.
Yeah, that's a good question. You're saying the distance of the sphere should enter, I think?
So I think it would be convenient to see that cylinder into the dilatation of the sphere. So in that picture, it is actually, we don't have any distance between spheres. But when we push down the cylinder to the plane, so it has a gap like 1 minus e to the minus beta. Can you draw the?
Yeah, I'm actually not sure which picture you want, but maybe we could discuss after if that's okay. Yeah, I just want to wrap up and then we can discuss. Yeah.
I just wanted to make sure to understand the limit. So is the beta much smaller than the radius of the spheres?
Yeah. The betas we're going to take to be very small. Yeah.
So when you say the red region that dominates, do you just mean the circle at the point where the 2 spheres touch? Because there are 3 points where the pairs of the spheres touch.
That's right. Yeah. So all 3 of them, yes.
But this red region you're referring to are 2 separate, so 3 separate.
Yeah. So we'll sum them.
You'll sum them.
Yeah.
But it seems to me that in this discussion, it only cares about a pair of spheres at a time.
That's right.
Okay, but that's not you say that's not a problem.
I don't think so. Yeah.
We have 3 circles that are touching, but there are many ways of drawing 3 circles that touch.
Yeah.
Where's the dependence on those radii and on the precise configuration of circles in the first expression?
Yeah, I think that there should be some expression here. This is maybe a bit schematic. Yeah, maybe I don't know, Jeha, if you have a better answer.
We also need to calculate the block to inverse the partition function. So if the position or radius of the sphere is different, then block also have a different shape. So at the end, if it inverse the partition function with these blocks, then the coefficient with OP coefficient will be same.
Yeah, yeah. I think this is quite schematic, and I should write a better formula, but I don't have it.
Yeah, but maybe my question is, it looks like a very simple formula for a complicated probability. Is it obvious that these spheres, it's normal, it's natural that it's related to something like what you wrote, but why would such a precise formula be computing this cartoon?
Why was it? Maybe I'm not quite sure. Like, well, I mean, the idea is that you just have these states propagating here, and they're propagating by length beta 1, beta 2, beta 3, and you're summing over these states. Yeah.
If you only have two spheres that are touching, do you reproduce the density formula you had
Yeah,
earlier?
yeah, that's right, that's right, that's right.
Only from, you say only by looking at this red region, that's enough.
Well, if you just have two spheres that are touching, like, then this is just Weyl equivalent to some, the original S1 compactification.
Okay, but I was asking specifically about this approximation if I'm using just the red region.
I see. Specifically with this approximation. I think yes. Do you remember, Deha? I think it does. If you just have two touching.
So, are you questioning about is it okay to consider only one red circle?
Yes.
Yeah, I think that's our assumption, and we don't have clear.
But I'm asking, in the case of just two spheres, you can check whether the assumption is correct by comparing to the previous calculation.
Yeah.
So yeah, when we are assuming there's only two cylinders, we are using same technique, like write down the effective Lagrangian.
Well, but the reasoning here is that you have an alternative approximation. My question is just whether this new approximation is consistent with the previous.
I think it is, but we can check it more carefully. Yeah, let me just wrap up and then we can discuss more. So let me just wrap up with some open questions and discussions. So the first, I want to talk again about the density of states. So we showed that at large j, large spin, but twist bigger than square root of j. So delta minus j is bigger than square root of j. Okay, this is assuming one j is turned on. With more j's, you can have this. We have some universal formula, universal entropy. It's also generally believed from things like light cone Bootstrap that if the twist is fixed at large j, the entropy should be determined by some mean field theory. So this rho should also be universal. So it's kind of a funny situation where at large spin, when the twist is order 1, you have some universal value. And when it's larger than square root of j, you also have some universal value. And the question is, when you glue these, like, let's say the twist scales as like j to the 1/4, for example, or something like this. Is this also universal or not? Like for a generic CFT, is it the case that like the way that these formulas are glued together is universal or not? Like, I think this would be very interesting to explore. So glue these formulas.
But in which sense it's universal? It depends like on a whole bunch of parameters. It's not universal at all.
That's right. But I mean the functional form. The functional form. But
yeah,
you're right.
But everything has a functional form. Even like take any OP coefficient, it's going to have some functional form.
Yeah, the leading term is a single number.
But it depends on f. Every CFT is going to have its own.
Every
f,
CFT will have a different one. But you of course you're right. But the functional form of J is constrained here. And so, are there similar constraints for intermediate values of the twist or not? Can we bound? Okay, then the next question I have is, can we bound some of these Wilson coefficients? C1, C2, dot, dot, dot. Maybe using these dispersive techniques or whatever. Like, are there positivity constraints on them, things like this. And the third thing I want to say is, in 2D, it was recently shown in a very nice paper by Scott and Tom Herdman and others that these Virasoro three-point function squareds are related to some wormhole actions, some on-shell wormhole actions. Is there any relation in higher D? It's probably not a clean yes, because in 2D, of course, you needed the whole Virasoro symmetry to make this very precise, and of course we don't have access to that in higher dimensions. But maybe you could ask, like, are there some particular combinations of these global primaries that will make it, or something like this. But anyways, I think this is a third thing to explore. And with that, so I'll conclude. So thank you very much for your attention, and I'll take any further questions.
Thanks. I see a few questions.
Oh, that formula there for the 3/2 to the 6 delta, it's valid in what dimension?
This is in, this one I think was in 3 dimensions. Yeah, we have some general D formula, but I think this one was 3D.
And do you have a similar formula to that one if the 3 deltas are different?
This one, yeah, I don't have it written down, but this one is written in the paper, but all of the spins need to be small. We don't have it for large spins yet, but that's something we can...
but you have for different deltas in the paper?
Yeah, as long as all the spins are small, yeah.
Okay.
You can shout, I'll repeat the question.
Is it possible to incorporate fugacities for global symmetries?
Probably, yeah, probably yes. Yeah, so you mean if I have a formula, for example, not just rho of delta and j, but like rho delta jq, for example. Yeah, I think it should be possible. We haven't done it, but I think that should be possible.
Oh, question in the back.
Can you explain why this OP coefficient is so big? I would have thought it would be small because it's.
Yeah, this is partly okay. Yeah, you mean like this 3/2 the delta thing?
Well, the exponential delta.
This is actually rho cubed times this. Does that help? Yeah, but if I divide by this will be small. I divide by e to the delta to the 2/3.
Thank you.
Yeah.
Any more questions? Question at the front.
You mean these Fs?
The F and the C1 and the C2, how should we measure them? It's like, you said that F can be measured in Monte Carlo.
Yeah, actually, I'm not sure how these guys did the Monte Carlo. One thing you can do, but it doesn't seem very efficient, but I think with more numerical data, it would be like, imagine you had a huge amount of operators, then you could just match the operators or the partition function with these. So I think like that would be one way to do it. I'm not sure like the more efficient ways, but. Yeah.
So that formula, as you explained, it's for global primaries,
yes.
right? And for Virasoro, you have a different result.
Yes.
Can you comment a bit on the dual interpretation of the two and how the dual?
Yeah. Good. Well, specifically for the case of ADS3, then where you have both. Yeah. For the Virasoro, it would really be like what I guess Matthew was saying, which is some black hole formation. If you do the global ones, like then it's much more complicated because then most of the states have a bunch of L-1s acting on them. They'd be L minus n's, not L minus 1, but L minus n's. So most global primaries will be like a Virasoro primary just with a bunch of L's. So it would be something like some black hole with a bunch of boundary gravitons exchanging each other. And like, apparently that's enough to qualitatively change the asymptotics of the answer. Because, well, I didn't write the 2D formula, but the leading behavior is much different. I think the Virasoro is like 27/16 to the delta, and then the Virasoro has a different power. So like, somehow, when you have these black holes with these boundary gravitons dressed, it like really qualitatively changes these scattering formulas or something like that. But I don't have much intuition other than just looking at these formulas.
I see. Oh, one more question. You have a minute.
So in the case of genus 1, somehow the thermal partition function gives the same result of modular invariance. So what if here that does not happen? So the actual result is not the one which is dominant compared to
the well, I guess.
In other words, if you try to do the two-dimensional computation, what goes different with respect to modular invariance?
What goes different?
So if you try to do the two-dimensional computation
yes.
with your technology,
yes. For density of states?
Yeah, can you compare the computation to the one you're doing with modular invariance?
Oh yeah. So I wrote this earlier, but you get the same result. So in 2 dimensions in this terminal effective action, when we just have this compact fine S1, then there's just a cosmological constant you can write down, and that's precisely when you identify F with the central charge, that's precisely the S dual of the vacuum character.
But modular invariance in the genus 2 partition function also guarantees you that
I don't think it works for genus 2 because it's this geometry is not a circle vibration. So, yeah.
All right, I think it's time for coffee, so let's thank the speaker again.
So just